Schneider. I will again briefly introduce you our speaker. Professor Schneider received his PhD in organic chemistry from Texas A&M University with Jeffrey Kelly, and then went on to the University of Pennsylvania School of Medicine, Department of Biochemistry and Biophysics, where he was a George Raises Fellow with William de Grado, studying protein design. In 1999, he began his independent career at the University of Delaware as an assistant professor of chemistry and biochemistry, and was promoted to associate and then full professor in 2009 with a secondary appointment in material science and engineering. He joined the NCI National Cancer Institute in 2010 as lab chief of the newly established chemical biology laboratory and was later appointed deputy director in 2015. He currently serves as executive editor of Biopolymers Peptide Science, the Journal of the American Peptide Society. His research focuses on biomedical engineering, biophysics, cancer biology, chemical biology, molecular biology, and biochemistry. He designs novel materials for regenerative tissue therapy and antibacterial therapy, and probably many more as well. And let's welcome Professor Schneider.
Oh, so maybe I should be...
That would probably be better, yeah.
I'm pretty loud. So.
All right. Get ready for some questions.
Yeah, you know, I want to start this afternoon by thanking the organizers for the kind invitation to come to Ankara. It's my first time in this beautiful city. I had a very nice tour yesterday of the old city. Oh. How's that? Way better. Okay. So I had a very nice tour of the city yesterday, and very happy to be here today to tell you about some of our science at the NCI and be part of today's Nanoday. So being the last talk, I'm fully cognizant of the fact that you are probably very tired and sleepy and probably need to be entertained a little bit. So today I'm going to tell you a serendipitous discovery story. One of my students made a discovery by mistake, and I'll tell you about that story. But I also want this talk to be a little interactive, to keep you involved. So I'll be asking you some questions during this talk, which means you have to stay awake during this talk, right? So my group invents new materials, mainly for therapeutic delivery and tissue regenerative therapy. So as it turns out, small molecules, proteins, nucleic acids, and cells, these represent therapy types that can all benefit from being properly delivered in vivo. And as many of you know, delivery vehicles can improve the in vivo stability of these therapy types. They can offer controlled and sustained release of these drugs. And if the drug delivery vehicle is appropriately designed, they can localize these therapies to targeted tissues. And all of these factors lead to lower dosing frequencies for patients, increased efficacy and lower toxicity for these therapy types. And this together improves patient compliance. And this is one of the main goals of the lab. Now my group, over the last 10 years, has been inventing new soft materials such as hydrogels and bioadhesives, as well as membrane-perturbing peptides to deliver all of those classes of therapies locally to tissue. The overall hypothesis that guides the research in my lab, much like the last speaker had mentioned, by understanding the mechanisms by which these materials are formed, understanding the mechanisms to molecular detail, these materials are degraded once implanted in vivo, as well as the underlying structure of these materials, again to molecular detail, that allows one then to design materials more quickly towards targeted clinical applications. Right? So if you understand your materials to molecular detail, that allows you then to redesign them for a particular application. Now, the material I'll be telling you about today are a group of gels that my group has been working on for about 10 years. We design these gels from self-assembling peptides, right? So macroscopically, the gels look like this. Okay? We design them from self-assembling peptides, where we design the primary sequence of a small peptide in such a way that it's intrinsically disordered when you initially dissolve the peptide in aqueous buffer and neutral pH and low ionic strength. Okay? So these peptides adopt an ensemble of radical conformations, which means they're highly soluble when you first dissolve them. So you can dissolve up 4 or 5 weight percent of the peptide in solution, and it'll have the viscosity of just pure water, right? So freely flowing. Now, we also design the primary sequence in such a way that it'll undergo a triggered self-assembly event in response to an environmental cue, right? So we can tell the peptide to self-assemble, and it'll trigger its assembly into a network of fibers, right? That encapsulates a large fraction of water, and that constitutes the formation of a three-dimensional viscoelastic gel. Okay, now, we have designed peptides to date that will self-assemble in response to changes in pH gradients, ionic strength gradients, thermal energy, light, metal ion binding, cell culture media, and even the actions of enzymes. Okay, the key here is that if you initiate or trigger gelation in the presence of a therapy, right, and this is this yellow circle, and that therapy could be small molecule, protein, another peptide, a nucleic acid, or even a cell, those therapies get directly encapsulated in the fibrillar network. You can trigger self-assembly in the presence of a therapy directly in a syringe, right? So now you have a syringe which contains a gel that's loaded with therapy. Now, these materials have a very special mechanical property that I'm not going to talk about too much today. That's their ability to undergo shear thinning but self-healing. So if you apply a mechanical shear force to the gel, you'll convert the gel from a solid-like gel to a viscous gel that flows. But after you stop the application of force, the gel reheals. Right? So that means now just by depressing the plunger on the syringe, you can thin the material through the needle, but when it exits the needle, it reheals. So once you've implanted now that material locally to tissue, the physical attributes of this fibril network then control the release rate of that drug to the neighboring tissue. Okay, and that's the whole premise of the technology behind these gels. What this means we can do is deliver drugs then topically through the action of the gel, subcutaneously, here's an injection into a cow leg, directly into organs, here's a direct injection into a mouse liver, and you see the gel here outlined. We can inject these gels either intratumorally or paratumorally, and we use ultrasound to guide the injection of the gels. So here you see a solid xenograft tumor here, right? And then surrounding it, you can see in light gray the gel. You can resect these tumors from the mice to demonstrate that that gel stays put exactly where it's been placed by the syringe. And what this allows you then to do is to deliver highly cytotoxic chemotherapeutics directly to the tumor mass where you avoid systemic toxicity. Okay? Okay, now, one thing that had always eluded our understanding of these gels is the exact molecular arrangement of these peptides in the fibrillar state, right? We had spent nearly a decade studying their mechanical properties, their optical properties, their rheological properties, but we never knew how the peptide actually self-assembled. And so I had a student, Kate Nagy, a PhD student in the lab, who started a collaboration with Robert Tico at the NIDDK at the NIH to use solid-state NMR to solve the structure of MAX1, the first peptide we ever designed in the lab, in its solid state, its fibrillar state by solid-state NMR. Now, MAX1, by way of background, is a small 20 residue peptide. We designed this peptide actually to fold into a beta hairpin conformation in the fibrillar state, where the beta hairpin is comprised of 2 beta strands, here and here, that are connected by a 4 residue, what we had designed to be a type 2' turn, centered at valine, D-proline, L-proline, and threonine. Now, the sequence in the beta strand regions is an alternating sequence of hydrophobic, here valine, and hydrophilic, here lysine residues, such that when the peptide folded, it would be facially amphiphilic. So one face would be greasy, and the other face would be water-loving. Okay? Now, I'm not going to show you all of the experiments that we did. I'm just going to show you the final structure because that's going to be important for later on in the talk. All right. So the peptide indeed does adopt a beta hairpin in its self-assembled fibular state. So for example, look at this light blue guy here. So here's one beta strand, a turn, another beta strand. The peptide self-assembles in such a way that all of its beta strands are in alignment as you traverse the long axis of a fiber. So here I'm just showing an octamer, okay? The long axis of the fiber would be in the plane of the board, okay? The peptide also self-assembles to form a bilayer. So the front monolayer is in greens and in blues, and the back monolayer is in pinks and reds. Now, the peptide self-assembles in a syn anti-molecular arrangement, and what that means is that with respect to each monolayer, the turns are on the same side, or syn, right? So here, 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 and here, and here. But anti with respect to the bilayer, right? Now, one of the cool things that sort of fell out during the structure determination of these peptides is how the beta strands packed with one another. Okay, so I want you to notice, say this blue beta strand right here. See how it's packed in between the two orange beta strands behind it? Sort of like a hot dog and a hot dog bun, right? That's very important. Does that make sense in Turkey? You guys eat hot dogs here? Good. In America, everybody knows what that means. All right. So what that means, in fact, is that the valine residues can pack highly efficiently with one another in the interior core of the fiber. So I've taken this fiber now, and I've rotated it, and you're looking down the long axis, right down the middle. And what you can see is the valine side chains here in CPK rendering pack very effectively against one another in the core of the fiber. So this is a very dry environment, so dry, in fact, that it excludes nearly all of the water from the interior of the fiber, right? This is important because this represents the thermodynamic driving force for the self-assembly and folding of the molecule as it gels. So follow me. If you imagine you initially dissolve the peptide up in water, it's unfolded, right? All of those hydrophobic valines have to be solvated by ordered water. And that's entropically unfavorable. When the peptide self-assembles and folds to form this very dry environment, it sheds that ordered water to bulk solvent, and that represents the entropic thermodynamic driving force for gelation. All right? Now, Kate, who determined the solid state structure, she also had a side project. And that's where things get a little bit more interesting. Okay? So her side project was to try to control the rate at which these gels were resorbed by the animal once injected. All right? So their bioresorption rate. And she came up with a simple idea of how to control that rate, and that was to make composite gels comprised of the parent peptide, which contain almost all L stereochemistry residues, with a mirror image peptide that contained almost all D residue amino acids. And the idea is that, you know, we all know that a peptide sequence with D residues should not be susceptible to proteolysis. So the idea is the more Dmax enantiomer you have in the composition, the slower the rate of bioresorption should be due to proteolysis. Does that make sense? Okay, so in fact, she did a real quick assay just to see if this was going to work. And here's just a trypsin digest assay. And you can see that a gel composed of 100% parent peptide max1 is degraded over days, right? But as you start to dope in the enantiomer, Dmax, until you get to 100% Dmax gel, you limit the rate and the extent of proteolysis. All right? So the idea worked, and that's all well and fine, but that's not really interesting, right? Because you would have predicted that. Kate is a really careful experimentalist, and she measured the mechanical rheological properties of each one of these compositions. Okay? I'm going to show you some of that data, and here's where the serendipitous discovery came to play. Now, what I'm going to show you is an oscillatory rheology experiment. How many of you know what rheology is? Okay, so quite a few. That's good. So what we're going to do is we're going to measure the onset of gelation as a function of time in a time sweep experiment. We're going to measure G prime, which is the storage modulus or an indication of how stiff the gel is. At time 0, right, we have a solution of pure max 1. And we're going to trigger gelation. The peptide self-assembles to form a fibular network, right, over the time course of about 2 hours. And here we're going to use buffer conditions where the rate of self-assembly is slow enough to follow conveniently in the rheometer. So after 2 hours, you get a gel of about 200 pascals. And to calibrate you, that's the stiffness of Jell-O, right, that you can buy in the store. Now, we're going to do the same time sweep experiment, but now with 100% Dmax 1. This is a 1-weight percent gel, same number of peptides in solution. What should the data look like? Anybody? Same, right? Very astute member of the audience. And in fact, it's the same, right? Now Kate's going to do the exact same experiment with a racemic mixture. Now, for the non-organic chemists in the audience, a racemic mixture is a 1-to-1 mixture of the enantiomers. Okay? 1-weight percent, same number of peptides available for self-assembly. We thought the data should look the same. But you can see how I've plotted the y-axis. This is what we saw. So the peptide self-assembled faster to form a gel network that was 4 times as mechanically stiff than either of the networks formed by either of the pure enantiomer peptides. Moreover, you can titrate this effect, right, by simply modulating the mole fraction of enantiomer in the composite. In this Job plot, you see at a 0.5 molar ratio, right, you get the biggest mechanical enhancement and rigidity. So that's the racemic mixture. So the question is why? So why is that? So Kate hypothesized that in fact, if she had a solution of 2 unstructured enantiomers, and here I'm just going to say they're purple and green, right, throughout the entire talk. So maybe this is L and that's D. She triggers self-assembly. One of 2 things can happen, she thought, right? These peptides could self-sort, right, and self-assemble into their own fibers. Those fibers could form an interpenetrating network, and that could lead to a stiffer gel network. Or the peptides could co-assemble into common fibers, and somehow that leads to a stiffer gel. All right? So now we're going to take a vote, and everybody's got to vote. And this is why I wanted everybody in the back room out there who's probably sleeping by now. They're not going to vote. So how many people think these peptides self-sort? Raise your hand. Raise it high. Be confident. All right? How many people think they co-assemble? A couple more. All right, let's see what happens. So Kate did a really cool experiment. She combined chemical synthesis and functionalization with transmission electron microscopy. And what she did is she took the parent peptide, MAX1, and she functionalized it with an azide that can chemoselectively react with a strained alkyne, so a click reaction. This strained alkyne basically coats a 10 nanometer gold particle. Then she synthesized the mirror image peptide, but now containing a biotin that can selectively bind to a streptavidin-coated 5 nanometer gold particle. Now what she's going to do is she's going to take these 2 peptides, let them self-assemble in the absence of any gold, right? She's going to take the resulting fibers and then add both the 5 and 10 nanometer gold particles. And if she sees by EM now fibers that only have 5 nanometer gold particles and fibers that only have 10 nanometer gold particles, that means the peptides have self-sorted, okay? But if she sees fibers that have both 5 and 10 nanometer gold particles, that means the peptides co-assembled, right? So this is what she's observed. You can't see anything. Don't even act like you can see. So what she did, things are too small, right? You can see the 10, you can't see the 5. We false colored the 5 red, you still can't see them. So she counted the number of fibers that bound only 5, the number of fibers that bound only 10, and the number of fibers that bound both 5 and 10 nanometer gold particles, right? And so what you can see is that in fact these peptides co-assembled to form common fibers, So whoever voted for co-assembly, you're batting 1,000. Okay? Now, the question is, why do these fibers form a gel that's more mechanically stiff? Right? So we turn our attention to polymer physics, specifically Mackintosh theory of semi-flexible networks, which tells us that the storage modulus, or the mechanical rigidity of a bulk gel, primarily rests with two adjustable parameters. Okay, the bending modulus of the fibers that make up the network. The bending modulus is related to the persistence length of the fibers, right? So the stiffer the fiber is, the longer the persistence length, but the stiffer it is, the more stiff the gel, right? The other parameter is the mesh size. So the mesh size is the average pore size between the fibers. The more cross-links you have in a network, the smaller the mesh size. The smaller the mesh size, the more mechanically rigid the gel, right? So now I'm going to ask you another question. How many of you think that these co-assembled fibers form a network that has more cross-links in it? Raise your hand. Makes sense, right? Because you make a polyacrylamide gel, you add more chemical cross-link, or it gets stiffer, right? That's what I thought. I'm always wrong, though. How many of you think you form stiffer fibers? Come on, you got to vote. Okay, like 7 people voted. All right. I was going to make a joke, but I'm not going to make that joke here in Turkey. So the first question we're going to answer is, are we forming more crosslinks, right? And we're going to use small angle neutron scattering. Not all of you might know what this is, so I'll give you a brief tutorial. So here we're going to take a gel, and we're going to irradiate it with an incident beam of neutrons. Now the mesh size, right, that's formed from those fibers is of a length scale that it's going to scatter that radiation. And it's going to scatter it according to some angle theta. When it hits the detector, theta corresponds to a scattering vector called Q. We're going to measure the intensity of scattering as a function of Q. And it turns out that Q, the scattering vector, is related to distance in real space by this simple equation, 2 pi over Q. And I'm going to graphically express that relationship here. So as you increase Q in reciprocal angstroms, you decrease distance in real space. All right? And I'm going to refer to this little chart throughout the next couple of slides. So we knew from earlier studies that the average mesh size of a pure Max 1 gel was about 30 nanometers. And we hypothesized that if these co-assembled fibers were forming a network that had a smaller mesh size, you ought to see a change in the scattering intensity centered right around 30 nanometers, which is right around 0.01 to 0.05 reciprocal angstroms. Okay, does that make sense? So here, now I'm going to show you real data and then calculated data. The real data is in green. Okay, so here's the scattering intensity as a function of reciprocal Q. And in green, this is the data for a pure Max 1 gel. Right? 30 nanometer pore size. We calculated what the scattering intensity should look like if we decrease the mesh size to a corresponding amount that would result in the 4-fold increase in rigidity. And that data is in blue. So that's the calculated data. So now I'm going to show you real data. Okay? Now before I show you the real data, I got to give you a little story. Okay? So Kate is a graduate student in the lab, and she's at the end of her 5th year. So in the States, typically the end of the 5th year is kind of the end of the road, right? Students start to change a little bit. They not so much like their advisor. My jokes are no longer funny. She wants to leave. She's tired of her colleagues. She quit cleaning her hood. She wants to go. So she really wants to see the blue data. Right? Get this thesis over with. So here's Max 1. Okay, now she's going to do the experiment with pure Dmax 1. And what should we see? Same thing, right? And she does, gratifyingly. So now here comes the Racemic gel. And this is what she sees. Oh, no. So we're not forming more crosslinks. Kate is a Wiley student, and she didn't show me this data for about a week because she should have figured out how she was going to present it to me. And she came into my office and she said, I got great news, Dr. Schneider. I go, what? She says, I figured out why the co-assembled fibular gels are more stiff, right? She said, because the fibers are more stiff themselves. And I said, well, how do you know that? She says, because the SANS data came back null. I said, well, okay, probably because of the theory, right? Since we're not forming more crosslinks, we must be forming stiffer fibrils. But the way science works is that you actually have to measure the stiffness of the fiber. So she says, well, how do we do that? Well, you can imagine doing this by force measurements, by AFM, but it turns out that the fiber diameters are too small. They're only like 3 nanometers, right? So we couldn't use AFM. Kate started a collaboration with Eric First at my old university, University of Delaware in chemical engineering. And Eric is basically, he's developing diffusing wave spectroscopic methods that can actually measure the stiffness of fibers. And the way he does this experiment is he embeds about 1 micron polystyrene beads in a gel, right? And he's going to measure, using super fast CCD cameras, the displacement of these beads within the fibular network. And the theory says that a bead ought to wiggle more by Brownian motion if it's surrounded by fibers that are less stiff than if it's surrounded by fibers that are more stiff. Okay? Simple theory. Oops. Turns out the frequency of that displacement is related to the persistence length of the fibers. The persistence length is related to the bending modulus, and the bending modulus is again related to the bulk stiffness of the gel. So I'm not going to take you through all the data. I'm just going to show you the answer in this table. So the persistence length of fibers formed by pure max 1 are 7.5 nanometers. The persistence length of fibers formed by the mirror image peptide is 7.5 nanometers, as it should be. But now look, the persistence length of the co-assembled racemic fiber is almost twice as large at 12 nanometers. You can calculate the bending modulus. You can use that bending modulus and then calculate the storage modulus. And what we find is that the racemic gels, right, they are more stiff because the fibers that form them are more stiff themselves. Okay? So those of you who have said, well, the peptides co-assemble into a common fiber, those fibers are more stiff than the fibers formed from either of the pure enantiomers are correct. Right? So now, Kate is very happy, and she comes into my office and she says, can you give me another year of funding? Because now I want to stay. Because why? So why are these fibers more stiff? And she said, well, it's got to be the way that those enantiomeric peptides pack together, right? So in fact, she said, look, even though those peptides co-assemble into a common fiber, they could self-sort with respect to the monolayers, right? And the molecular packing could lead to a stiffer fiber somehow. Or the peptides can alternate as you go down the long axis of the fiber, but pair up across the bilayer, right? Or they can alternate going down the long axis of the fiber and alternate going across the bilayer. So either one of these three. Now I'm not going to show you all the data because of time. We used, what's that?
What about interdigitation?
This? Yeah. Could be. This is interdigitation. So we use solid state NMR coupled with isotope edited FTIR measurements to solve the structure. So now we're going to do one more vote. Interdigitation like this, you mean? Yeah, there's no room.
Okay.
Right? Because you only have 4.5 angstroms in between each strand. And that's the hydrogen bond. Okay. So how many think A? Door A? One guy? All right. Door B? Nobody. Oh, yeah, 3. Okay. C? No. That's why I did so bad on all my exams. It's actually B. Yeah. So look, they alternate going down the long axis, but they pair up going across the bilayer. So now the question is, why does this lead to a more stiff fiber? So then we use molecular modeling to gain insight into that question. And now I'm going to show you just a very simple ChemDraw model to start the argument of just one dimer from one of the monolayers, okay? So here's a ChemDraw model of just a dimer. So this is the L peptide, this is the D peptide, right? And so what I want you to notice is that within each beta hairpin, the two beta strands are arranged in an anti-parallel fashion. So one of the strands goes from its N to C terminus and the other one goes from its C to N terminus, right? That dictates the formation of linear hydrogen bonds, which I've not shown in the hairpin. But what I want you to see across the dimer interface, now these two beta strands are arranged in a parallel fashion, right? And if you remember your protein structure, whenever you have parallel beta strands that make a sheet, you are obliged to form bent hydrogen bonds. Those bent hydrogen bonds dictate the strand registry and alignment of the strands in the sheet. Okay? Not only that, they have another job, and that is to dictate where and how those valine side chains are placed into the core of the fiber. And they are placed into the core of the fiber in such a way that they can form what we call staggered, nested hydrophobic interactions. So staggered, you see here, 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 here. Nested, meaning if you pick one valine, its neighbors across the sheet, right, are on either side of it, and it can form a nested interaction like a bird sitting in a nest, right? This type of staggered hydrophobic packing increases the van der Waals contacts, and it's a very effective and stabilizing mode of packing for beta sheets. Now, if we look axially down the long axis of a fiber, right, you pick any purple valine side chain, it's always surrounded by two green guys. You pick any green guy, it's always surrounded by two purple guys. Okay? Very effective mode of packing. Now I'm going to compare this to a situation where we have now just pure enantiomeric fibers. Okay? Now across the dimer interface, you see that these guys are arranged not parallel, but now anti-parallel. That dictates the formation of linear hydrogen bonds, which dictates that the valines now pack on a face edge-on interaction, pairwise. Okay, so they're unable to form this nested hydrophobic interaction. Okay, so if you go to the protein data bank and you ask yourself the following question. In beta sheet-rich proteins, which contain valines, how do the valines pack with their neighbors? It's almost always like this. It's almost never like this. Okay? So this is very stabilizing. Now, this is not a bad mode of packing, right? Because I showed you the NMR structure earlier. It's pretty good, right? But it's just not as good as this. Okay? Here's actually now looking down the fiber. Every green side chain, its buddy across the sheet is directly behind it, face on. Okay? Now, so the answer is the racemic gels are more stiff because the peptides co-assemble into common fibers that are more stiff themselves. Those co-assembled fibers are more stiff because of the packing mode, which allows these valines to pack more effectively, and that locally stiffens the fiber going down the long axis of a fiber, increasing its persistence length. Does it make sense? So Kate and I were very, very happy about this result. She wrote the thesis, she started to write the paper, she did her literature search, and she found a very interesting paper. Okay? From 1953 by our old friend Pauling, who predicted, this guy must have been amazing, right? He's predicted your stuff, he's predicted my stuff. He predicted that if you take a beta strand composed of D residues and a beta strand composed of L residues, they'll form what he called the parallel ripple beta sheet, right? So they can co-assemble, form bent hydrogen bonds, right? So why did he call it the rippled beta sheet? Well, I'm going to turn this by 90 degrees, okay? I'm going to call your attention to the two C alpha carbons here in the peptide backbone. So one enantiomer is going to the left. The one C alpha from the other enantiomer is going right Now conceptually, I want you to add a D and an L peptide sequentially coming out of the plane of the board. Now these C-alpha carbons form a wave or a ripple. And that's what Pauling termed the rippled beta sheet. Okay? Now if you look at our dimer, it's here. We form the bent hydrogen bonds. It's parallel. We can rotate it by 90 degrees, and you see that our C-alpha carbons rotate or alternate left and right, left and right, left and right as the fibril comes out of the plane of the board. So the overall arrangement of packing was actually predicted by Pauling over 60 years ago, but what he had failed to realize is that the packing not only dictated strand registry and the alternating sequence of L and D isomers, but it dictated where the side chains of the residues were displayed on the face of the sheet. And in fact, every one of his models in this paper were void of side chains. He only showed the main chain. And in fact, we contend that the most important factor is how the side chains are propagated into the sheet face and how they can pack with their neighbors. And that's what leads to the demonstrative increase in rigidity that we observed in the gels. Okay, now, I'm going to change focus just a minute. I have a couple more minutes. Sure.
You mentioned about the Racemic mixture, but what happens if you keep one is 60%, one is 40%? Do you still observe co-assembly or?
So we don't know exactly because we haven't solved the structure of those mixtures. But I showed you the Joe plot where we've made those mixtures. What we think is happening is that under thermodynamic conditions of self-assembly, you'll have co-assembly until you run out of the rate-limiting reagent. And then basically you get monodispersion of the leftover enantiomer. Now, is that exacting? Probably not. You'll get some partitioning in between the two modes of self-assembly. Does that make sense? Okay, now what I want to show you, back to the hypothesis in the lab. So why do we take all this time to try to understand the behavior of these gels to molecular detail? And the reason is because we want to make stuff that has clinical applications, right? And if you don't understand your materials, how are you ever going to design a material for an application, right? So by now, I hope I convinced you that the packing of that hydrophobic interface in the core of the fibril is very important, right? And we're going to take advantage of that in the next section of the talk, which is a lot shorter than the first section, so it's okay. Now, we were approached by a group of plastic reconstructive surgeons at Johns Hopkins to invent a new material that would help in clinical application of theirs, namely anastomosis. Okay, so Gerald Braddockard, his group at the Hopkins School of Medicine, is probably one of the world-leading groups in whole hand transplant surgery. Okay, so when a donor hand is mailed to Hopkins to be placed on the recipient arm, it's void of blood, right? The surgeons then connect that donor hand to the recipient arm, and it turns out one of the things that dictates the success of that transplant surgery is the number of blood vessels you can successfully suture together, or anastomize is what that's called, okay? Now, a gifted surgeon can suture together blood vessels that are on the order of about 1 millimeter in diameter. Okay? Now remember, these blood vessels are void of blood, so their lumen, which would normally be open, is now collapsed. So if you're a surgeon, right, imagine passing a needle through one wall, okay, of the vessel and out the opening of the lumen without catching the opposing wall. Because if you catch the opposing wall, you tie off the end of the vessel. Blood can't flow, you get ischemia of the tissue, and it dies, right? So that's exactly what they don't want. They approached us and they said, could you make us a gel that would increase the patency or the rate of success of these suturing processes, right? Now, here's where it really gets interesting. He said, not only are we really good at hand transplants at Hopkins, but we're one of the only places in the world that do microsurgery or microanastomosis. And now that is suturing together blood vessels that are microns in diameter. Okay, so take a human hair, a couple hundred microns, right? and now suture that to another human hair. And that's what his group does. So we invented a gel that could basically be shear thin injected into the collapsed lumen of these microvessels, plump them up, act as a mechanical stent. We inject the gel in the interspace between the two vessels to help approximate the vessels to aid in the suturing process. It's a shear thinning gel, so the needle can be passed right through the gel, right? You can install the sutures, wash away the exterior gel, but now you got a problem because you got gel in the middle of the vessel. And if you let the blood flow, it's going to hit the gel. You'll get thrombi formation, ischemia, and the tissue dies, and that's exactly what they don't want. So we invented a gel, designed a gel that would undergo a reverse phase transition from gel to solution in response to either UV radiation or two-photon radiation. Okay, so how do we do that? We're going to take advantage of that dry interface in the core of the fiber, and we're going to basically incorporate into that core a photocaged glutamic acid. And we're going to cage the glutamic acid with this 4-methoxynitroindolin group, which is a greasy hydrophobic group, which likes to hang out in that core interior environment. But when you shine light on it, it pops off, and what you're afforded is a glutamate side chain. Not a glutamic acid side chain, but a glutamate, the formal -1 charge. Now we all remember our biophysics. If you develop a glutamate, -1 charged residue side chain in the core of the fiber, which is void of water, which could otherwise solvate that charge, what do you think is going to happen?
Coulombic explosion.
Coulombic explosion is exactly right, and that's what our hypothesis was, because the system ought to disassemble to solvate that negative charge. And in fact, that's what happens. Here's the peptide we designed. It's called APC1. I won't get into the design specifics. The first experiment we did was a rheological experiment just to see what the behavior of the gel would be like to approximate its clinical use, right? So in the rheometer, we trigger gelation. We get a nice gel that's about 2,000 pascals. In phase 2, we shear thin, and we see that the gel self-heals, and that basically mimics being delivered from the syringe into the lumen of the vessel where it has to reheal and act as a stent. And then we basically shine light on it through, we have clear optical plates in the rheometer, UV irradiate the gel, and you see that we can destroy the gel and turn it into a viscous solution that flows. So it looks like it's going to work. So then we did some just real quick biophysics experiments to see how long it would take to decage the residue in the gel. It's about 90 seconds. So the physician puts in the sutures, takes a handheld UV, or if you want to get fancy, you could use two-photon radiation. But handheld UV works great. 90 seconds, it pops off, right? Okay, now what happens to the fibril network? So we looked at it by EM just to take a look at the two-dimensional display of fibers plated on a surface before and after radiation. So here's the fibril network that we take out of the three-dimensional gel and just plate on a two-dimensional surface, and we just grossly measure the fibril lengths, and you see that we have 3 manifolds, 2 down here in between 200 and 450 nanometers, and then these guys up here at long lengths. You irradiate the gel, isolate the fibrils, and you can see that you can transform all these long guys into shorter guys. So that's a good indication that this is going to work in the animal. So then we went to the animal model, and we're going to use a mouse femoral artery anastomosis model. And in this model, we take mice, we isolate the femoral artery, either one in either of the back hind legs, and we nick it. So we sever the artery, and then we use optical coherence tomography, and you're looking end-on at the femoral artery. And you notice 2 things. The first is that it's about 200 microns in diameter, which is incredibly small. And the second thing is that the lumen is collapsed, right? So now the surgeon is going to inject the gel, right, into the ends, and in the inner space, you can see that we plump up the gels very nicely. So it's a very nice mechanical stent. We can use the gel now to approximate the 2 vessel ends, get them close together through that shear thinning medium. Here's an actual view of it. So the surgeon puts in the sutures, hits it with light, and now you can see blood can flow unrestricted through the sutured site. We can use volume Doppler OCT, and we can measure the rate of blood flow, and that's indicated in reds and yellows here in this false color image. And we can quantitate that, and I'm just going to show you. In this experiment, we did anastomosis without gel, the anastomosis with the gel, and then we measured the speed of blood flow in naive tissue, so above the suture site, there's no difference. Importantly, at the suture site, right? So here's the anastomosis without gel. You see that you have severely restricted the blood flow here, and this is representative of many experiments. But with the gel, you restore blood flow through the suture site, and then downstream, we actually have better blood flow than you doing the anastomosis without the gel. Now, so I'm pretty much on time. Got one more slide, I think. So we were really happy with this work. We wrote it up, and we sent it off to the journal. And we got 3 nice reviews back, as nice as they ever are, right? But 2 of the guys said, yeah, this is really interesting, but when you irradiate with light, we're worried that you're not destroying all of the gel, and then you're going to get microparticles that could go to the very, very small vasculature of the mouse, quote, in the toes of the mouse, and make thrombi, and it's going to be detrimental. So you have to demonstrate that you're not clogging up any of the other vessels. So Gerald came up with this great experiment, great for humans, not so great for mice. So what he's going to do, have you guys ever heard of microfilm polymer? So you ever been to the museums where you see the anatomical human beings and you see their vasculature, right? What they've done is they've filled their vasculature with this setting polymer. It's a liquid, but as it flows, it sets as a solid, and that's what you're seeing, right? The vasculature. So what Gerald did with these mice is he performed the anastomosis with the gel, irradiated, right? They're sleeping. He wakes them up, lets them run around for 4 or 5 hours, and he takes those poor mice as they're alive, and he perfuses their heart with microfilm polymer. And the key here is that the mice are alive, their hearts are beating, and they will beat that polymer wherever it can go, and more importantly, you'll see where it can't go, right? So if there's an occlusion from the gel, the polymer won't be able to access that vasculature. So here's the experiment. So here's the suture site here, right? The animal has pumped the microfilm polymer all the way down through the suture site into the very small vasculature of the toes. So this was awesome. So we wrote it up, and we sent it back to the journal, and they sent it to the 2 outstanding reviewers at this point. The one reviewer came back and said, this is great. There was that last guy. They said, it's nice, but I still can't see very well down in here. It's not fine enough resolution. So then we finally put the last nail in the coffin. We did high resolution micro CT, and I'll just show you a very just quick movie to end the talk. Basically what I want you to see is now the polymer fill in the vasculature in the toes all the way to the tippy tips of the toes, right? So now finally the reviewer said, okay, this is good to go, and they published the paper. So with that, I'm going to end the talk, and I hope I convinced you that if you're making nanomaterials, or in this case micromaterials, if you will, that understanding those materials to the greatest extent you can really enables you then to more quickly design materials towards a targeted clinical application, right? So we know these gels now so well that I can tell a surgeon who comes to me and says, can you do X with these? And I can honestly say, well, no. So maybe you should use another technology. Or I can say, yes, give us a couple months to figure it out, right? So with that, I'm going to end. I'm going to thank again the organizers for inviting me here to this very great day, and thank my group. It's a small group, but of very talented postdoctoral fellows. The work mainly today was from Kate Nagy, who's now at Merck. Some of the later work I showed you was from her husband, actually Dan Smith, who's now at GSK. Gally Fitchman here is actually Israeli. I know there's some Israeli folks in the audience, and she was in Ehu Gezit's lab for a PhD and is now in my lab. I don't have any Turks in the lab right now, but maybe we could change that. Huh? Oh, I did have a Turk, Jem, but he's graduated now, right? So he's now off to a startup company up in New York. So okay, with that I'm going to end. I'll thank you for your attention.
Thank you very much, Joel. Now we can have some questions.
I did ask him a lot of questions during the talk.
What about cross-linking? You did any cross-linking with your peptides? So what's the effect of cross-linking? Is it better or is it worse?
So, so typically if you cross-link these networks, for example, what will happen is normally we cross-link the lysines because that's the easiest thing, right? So that'll stiffen up the gel quite a bit, but it affects their shear thinning self-healing properties. So it turns out that if they're cross-linked and you shear thin them, they can't self-heal very well because they can't find their place back into the gel network. So that's mainly what happens.
But for example, if you want to use these things, for example, knee or something in the body, so you need something.
Yeah, you would never use these in the knee.
Why?
Because they're too soft. And there's actually a lot better materials to use in joints that have large compressions and shear forces.
Even then cross-link?
There are still better materials that I would use, not my materials, in the knee, for sure, right?
Yes, wonderful.
Thank you.
I know there is always a concern of how the body is going to get rid of these ejecting materials. So you show that indeed it really comes to the pinpoint, of the fingers. But what about the position of it out in the body?
Yeah, so largely they're proteolyzed. The L isomers are, and those are secreted in the urine. The D peptides, so it turns out that there are enzymes that can change the stereochemistry. So what happens is that you have those enzymes that change the stereochemistry. They get cleared more slowly, right? But it's a great question because in the field of peptide therapeutics, a lot of folks will argue, well, if you want to increase the half-life of a soluble peptide in circulation, you basically make the mirror image. And what we found, and this is probably sequence dependent, but what we found is that if you inject just the D peptide, in this case just the hairpin, it has a really hard time clearing at a, not optimal, but even at a normal rate that would ensure that it's cleared. And what happens is it deposits in the kidney, and then you get basically failed kidneys. So you have to be very careful with how much enantiomer that you have in the composition, right, for these materials, and just in general in injecting peptides. Does that make sense? Did I answer your question?
I know it's very problematic also for colloidal nanoparticles if you want to use them.
Yeah, I mean, and I will say that it's probably particle dependent, right? The biodistribution is how it's cleared, and we all know that. But there are tricks that you can play to get it to clear, Yeah.
Yes,
Thanks for this great talk.
You're welcome.
I want to ask if you use for these hydrogels for other therapeutic applications, for example, drug delivery or.
So we do. I don't know if it's a little maybe late in the game here, but so we mainly use these to deliver protein therapeutics. And at the NCI, we use these to deliver cytokines, interleukin 7, interleukin 15, to basically control the maintenance of T cells in CAR T cell therapy and in TIL therapy for immunotherapy applications. With some very exciting recent data on that. It's not ready for prime time yet, but we've gotten the provisional patents in, so I can talk about it now, but it's not good enough to show. And then most recently, we've designed delivery systems, and I'm just going to show this real quick, for mesothelioma. And so this is a lung cancer that's caused by asbestos, and we heard about asbestos today. So mesothelioma is a pretty nasty cancer that occurs between the wall of the chest cavity and the lung. and it occurs in sheets. And so when the physician removes it, they deflate the lung and basically have to peel off the sheet of cancer. And it's a really crude resection therapy, and it always leaves a microtumor. And so we've invented a gel that can be shear thin injected into that cavity so that when the lung is reinflated, the gel can thin out of the way to the natural shape of the lung and then coat very effectively the cavity of the chest wall, right? And we can deliver RNA nanoparticles, and these are therapeutic RNAs, and we've done a lot of work. This is going to come out in publication maybe in the next few months, hopefully if it's well received by the reviewers. But these particles are uptaken by endocytosis. They're released from the early endosome. They release the RNA, and then it targets genes that are responsible for the apoptotic machinery in mesothelioma cells. And so we can effectively shrink tumors, for example. But so we do deliver therapies with the gels. But it didn't fit into the story I told you about the fibrils.
Right, so let's give Joe another round of Thank you very much.
Thank you.
Now we will proceed with the final section, which is the closing and the award ceremony. So I won't have a closing talk. And all of our speakers have done the job basically for today's event. So they have presented great research. So I would like to again thank all of them. And I appreciate very much their presence and also your participation to the event. I have to buy some time in the meantime. So, so we will start with nano art, I guess. Okay. I'm not a very big fan of announcing awards, because basically, you know, announcing 3 winners means mathematically announcing 30-something non-awardees. But please look at it this way. So sometimes science is underrated. So we need to really create opportunities where we demonstrate that we value and appreciate science. And this is basically just one little opportunity for us to show that. So it's nothing to mean that, you know, we are only selecting these 3 and rejecting the rest. So these whole awards and these type of gifts just serves to a much bigger purpose. So just think of it that way. My role in our group is also psychological consultancy in our research group, so I'm pretty good at it. All right, so without further ado, to present the awards, I will kindly ask our speakers one more time to the stage, maybe for the Nano Art Award, Efrat and Joel, if I may take you again to the stage. So again, as usual, we will have 2 runner-ups and 1 winner. Excellent. Şunu mu alıyorum ben? All right, so we will start with the runners-up. And also, this is the first time that I'm seeing the results in real time. So the first one is Ece Uslu from Middle East Technical University. All right, Ece, if you can stick around, maybe we can take a photo all together. So the second one is Engin Can Sürmeli. That's exactly what I meant. Thank you. And the winner of 2018 nano art contest is Wild Gorilla. Çağatay Mert Oral. Or you expect for this, right? Of this one. Now we will proceed with the poster awards, and for that I will ask Banu Hocam and Reshef to the stage to present the awards. All right, so the first runner-up for the nano poster contest is Elif Duman Ergül. And the second runner-up is Yemliha Altıntaş. If she is away, you know, a friend of hers may take the award. I guess she's not here, right?
I'm second Oscar, so I think we'll come back.
Sure. What about the third and the fourth authors here? So this is all right, and the winner of 2018 Nano Poster Award is Ziya Işıksaç. Well, maybe a picture altogether. All right, and with that, I'll be closing the Nanoday 2018. And again, I would like to thank all of you for your participation and for the whole joy throughout the day. Thank you. Just one quick announcement. So for those of you who have signed up for the open house event, that would be better if you can remain seated in this room. For those of you who signed up for open house to visit the laboratories. So just remain in the room and we will be arranging it in a few minutes.